Section 3.5 is where we start to talk about naming. And we're going to start with some simple ionic naming, where we're going to just talk about the cations and the anions by themselves and give them English names. And in compounds, we want to be able to recognize what the cations and the anions are by where they're listed. Cations being listed first and on the left, anions being listed after. So the first thing we have to do with that for cations is decide if we're looking at a constant charge or a variable charge cation. For constant charge cations, we have most of the non-transition metal cations plus 3 that are actually transition metal cations. And these you can just either memorize or look at basically by where they are on the periodic table. And on the second table that we have you memorize, there is an additional set of variable charged ions that are from the transition metal or middle section of the periodic table, and these metals can form cations of different charges, such as +2 and +3, or +2 and +4, or +1 and +2. And the system we're going to use for naming these involves using a set of Roman numerals after the name of the element to designate what the charge on that ion is. Now, we have an older system using us and ick for saying less charged and more charged, but that's not something you're going to really see in this book. We're including it here only because we want to make sure that you see that there is this other system in case you run into it later. When you're naming cations, you simply name the element. That's all there is to it. So if the charge does not change, then you just name the element. So Ca+2, it would just be a calcium ion. If the charge is variable, such as you have iron 2 and iron 3, then you name the element that's part of the ion, and then you put the Roman numeral that represents its charge. So this would be the +2, and again write the word ion. So if I wanted to indicate the +3 version, I would put Roman numerals 3 and the word ion. Voila, it's just that easy. Anions are basically not any harder, but when we name anions, we use the root of the name. So for chlorine ions, we start with chlor, and then we change the ending to IDE to represent that it is an anion, a negative ion, and again write the name ion. So if we had oxygen, we'd put ox as the root, IDE as the ending, and the word ion again to say that this is an ion all by itself. To name a compound, an ionic compound, and remember we know it's an ionic compound because we have something on the left side of the periodic table combining with something from the right side, a metal and a nonmetal. That's what makes an ionic compound. That's how you can recognize that this is the sort of rules you should use. All we do is name the cation and then the anion. So KCl would be potassium chloride. And K2O would be potassium oxide. So we leave out the word ion. We don't need to write the word ion if it's not an ion by itself. It's just ions combining to form a compound. And otherwise, you just name the ions involved. Notice we have a 2 here. The reason we have a 2 there is because as we're naming, we have to be able to tell, that was a horrible handwriting there, we have to be able to tell that there's a charge balance present here in this molecule. So potassium and oxide, K and O, don't have a 1-to-1 ratio because potassium is +1 and oxygen forms -2 ions. So therefore I need 2 potassiums for every 1 oxygen. Okay? Similar in a way to H and O in water. If we think of this as ionic, and it's not completely ionic, but we'll talk more about that later. Oxygen being minus 2. Write this up here. Oxygen being minus 2 with hydrogen being plus 1 means that I need 2 of the plus 1 hydrogens to have a total of plus 2 charge to balance out the minus 2 charge of the oxygens. Okay, so it's a little more complicated basically to translate back from the name to the formula than it is from the formula to the name, because we don't have to mention the subscripts when we name things because there's only one possible ratio, and that's dependent on the charge. Now when there isn't only one possible charge, such as iron 2 oxide, we have to indicate that the iron here is plus 2. So when we look at this molecule, iron 2 oxide, we know we have iron and oxygen. The 2 tells me I have a plus 2 charge for the iron. Where oxygen is on a periodic table tells me that's a minus 2 charge. So Fe and O are balanced with a 1-to-1 ratio, and we're fine. Now what if we have Fe2O3 as a compound? Now we have to figure out what the charge on the iron is. Oxygen is always minus 2, so where it is on the periodic table, meaning that 3 of them together gives me a minus 6 charge. Now this has to add up to 0 altogether. They have to cancel each other out, or else it's not a compound. So I have to have plus 6 on the cation side. Split between 2 irons means that each iron is plus 3. Okay, so that means when I name it, I have to tell people, because it's a transition metal, it's a variable charged cation, that this is the plus 3 species. I do that with parentheses Roman numeral 3. But otherwise, I name this exactly as I normally would for a compound. One extra wrinkle for this is that I have polyatomic ions as well. And these are ions that are made up of multiple atoms bound together covalently through the sharing of electrons, which we talk about in the next section. But since the overall species is ionic, with minus 1, minus 2, minus 3 charges, depending on what it is, then we need to be able to include this in the ionic naming rules. It's no more difficult if I have a compound like potassium chlorate. I know it's potassium chlorate because I named the cation, same as the element name, just like any cation. And then I see that there's more than one element making up the anion, so it must be polyatomic, multiple atom ions. So I memorize this table and I look at it and say, okay, ClO3 minus 1 is chlorate, so I name this potassium chlorate. And if I have something like calcium hydroxide, I know that there's no hydrox element, so this must be a polyatomic ion. So I look it up, or I have it memorized, which is what we have to do, and see hydroxide, OH minus, right here. So I know it's calcium hydroxide, and now like we do with everything, we balance it out. The hydroxide having a combined minus 1 charge means I need 2 of them to balance out the calcium. So the way I show that I have 2 of that whole hydroxide group is by putting a subscript of a 2 next to the hydroxide ion. And I have to write a set of parentheses around the hydroxide to say that I have 2 of the entire group of that species. Now, the chlorates and chlorites, there's 4 of these here. And this pattern of naming them, so we have the root chlor, 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 chlor. We have hypoite and ite and ate and per-ate. Is how we name from 1 to 2 to 3 to 4 oxygens attached to this particular root chlorine atom. Now, hypo means even less than normal, so that's where the 1 oxygen comes in. Ite means less, so 2 versus 3. 8 means more, 3 versus 2. And per, like hyper, means excess energy. Per 8 means even more than 8, or in this case, 4. Now, keep in mind, I can have sulfite, meaning less than the normal amount of oxygen, and have it be SO3 minus 2, just because the sulfate is SO4 minus 2, and there aren't any lower number of oxygen species for SO ions that we name this way. So it doesn't mean that if I have ite, it's always going to be 2 oxygens, or 8, and I'll always have 3 oxygens. But for this series of 4, that's the set of rules we have. Now, what I wanted to point out specifically about this series is we want you to not only memorize the chlorine-containing ones, but to know that the halogens all will do the same thing, have the same sequence. So fluorine, chlorine, bromine, and iodine will all have a series of 4 oxygen-containing species and be named in the same format. So fluorine, for instance, the one with 1 oxygen would be hypofluorite, 2 oxygens, fluorite, 3 oxygens, fluorate, and 4 oxygens per fluorate ion. And you could extend this pattern to bromine and iodines as well. Okay, so let's name these. We have NH4Cl. We name the cation, polyatomic, ammonium, and the anion, chloride. So together this compound is ammonium chloride. And if we have something like calcium nitrate, just means we have calcium and NO3, so +2 -1. I need 2 of these, so this would be the formula for calcium nitrate. So pause the video at this point and give all of these a try. Try naming all of these ionic compounds, and then we'll display the answers, and you can see how many of these you got right. And if you got some wrong, you can go back and double check what the rules are to see what to do differently. And there we go. So double check your answers, pause again, and then we'll move on. And so it's not really different. I originally intended to kind of go with names to formulas later, but we kind of did it as we went. So we know how to go from the names to the formulas. We just have to look at balancing the cations and the anion charges. All right, so that's the only added difficulty. So let's give that a shot. We've done it before, practiced in the earlier ones. Name, here's the names, give all of the formulas. And again, just like before, pause it. Okay, so let's look at the answers and see how many you got right. There you go. So double check these and make sure that you have all the answers correct. And if not, go back and look and see what you can do differently. Now, hydrates are really the only thing that we have left to talk about in this chapter, or this section, I'm sorry. And those are water molecules that are attached solidly to the crystal. This isn't just moisture content like dissolved species or something like that, or wet species. These are actually in the dry crystal. We have a certain number of water atoms attached in a certain ratio to that particular species. And the way we name those is we use a prefix for the number of waters, and then we use the word hydrate as the ending. So CaCO3 dot half a water, or star half of a water, is just calcium carbonate. Well, worst R ever. Carbonate. Hemihydrate. Hemi for half. Hydrate for water. And that's all one word. And here we have magnesium sulfate. sulfate, dihydrate, or 2 waters. Ammonium nitrate, hexahydrate, means 6 waters. And iron 3 acetate, iron and acetate, +3 for the iron, -1 for the acetate, means we need 3 of them to make this even out charge-wise. And then trihydrate means 3 waters. And that's it. That's as hard as this is.